Okay, hope everybody's having a good day. We have our third focus activity. We are turning these in next week. Wednesday is when I'm going to be officially looking for those. I think that's the 3rd of April. You can turn them in early if you want to. We will have 4. I haven't decided if I'm going to give it to you the 4th one on Monday or Tuesday, though, so definitely don't turn them in yet. But it's one of our last grades for the 6 weeks because next Friday the 5th is the end of the 6 weeks. What's going on tomorrow? Okay, you got an exam, okay, but it's over sequences. It's not over our current lesson of series, okay? No summation on there. Just find me this term, okay? Find me the common ratio, common difference, write the explicit, recursive formula, things of that nature. So basically, if you feel really good with the homework, you should be okay for that exam. It's just straight skills. I didn't put any word problems on there. Okay, just straight problems. In fact, the key is still making its way around. I'm going to pass back your papers to those who turned them in yesterday right at the end. And, of course, next week, we'll go ahead and hopefully finish up series pretty quick. We'll move into the binomial theorem. We got to take the district assessment next week. Now, next Thursday morning by 8:05, okay, that's the 4th, I believe, that's when everything outstanding is due. If you have a retake you want to take a look at, if there's a homework assignment you can still turn in, everything needs to be taken care of by next Thursday, 8:05. That way I'll go ahead and start getting the grades situated and get those submitted. Okay, I think that's all I got unless anybody has any questions. How many people right now, show of hands, if I were to give you the test right now, you feel 100% confident? So many hands going up. That's what I like to see. The confidence level is just through the roof. Okay. But you still have, one more night, one morning. If you want to come in, ask me some questions. I'll be here at 7:45. Okay. So focus activity number 3. So this one, I geared it towards arithmetic and geometric sequences because that's your exam tomorrow. So a little more practice. It says, number 1, find the general term a sub n. So when it says find the general term, that means find the explicit formula. Okay, we want this one here. A sub n is equal to the first term plus n minus 1 times the common difference d. And then, of course, we want to simplify that. So we're given the 7th term is 41, and the 13th term is 77. And there are different strategies to do this. I would probably go ahead and use the formula itself to help you solve for the first term and the common difference. So let me show you what I mean. Let's start with the 7th term. Now, because it's the 7th term, I know the value of n is 7, right? So I'm going to plug everything I know into this formula. So I'm going to say we don't know what the first term is, plus, but if I were to plug 7 in there, what would I have times d? Okay, 6d, because the 7 minus 1, right? Now, because I'm using the 7th term, I can set this guy equal to 41. Okay. Now, what I'm going to go ahead and do is solve it for the first term. I'm going to get that first term in terms of d. So 41 minus 6d is equal to the first term. So now I'm going to put this guy to the side for a second. I'm going to do the exact same thing for the other term. Okay, now it's the 13th term. So I know n is equal to 13. Okay. So I'm going to go ahead and say the first term plus, well, if I plug 13 in there, what would I be multiplying by d? 12. Okay, the 13 minus 1. And because I'm using the 13th term, I can set this equal to 77. And then I'm going to solve this one for the first term as well. So 77 minus, what am I doing here? Minus 12d is equal to the first term. Well, do you see where I'm going with it? What can I now do? Yeah. See, I know that each of these is equal to the first term. So by the transitive property, I can set one equal to the other. So 41 minus 6d is equal to 77 minus 12d. See, this will allow me to solve for the common difference. I could use that to find the first term. Then I can use that to go ahead and write out my formula. Okay. So now, it's just an equation. So I can move any of the 4 terms that you would like. What would you like me to move first? Okay. You want me to go ahead and move the 6d? Okay, so if I go ahead and add this one over, okay, then negative 12d plus 6d is a negative 6d. negative 6. Okay. So at the same time, why don't we go ahead and subtract the 77 over? So 41 minus 77, negative 36. Okay. And now we can easily solve for D. In fact, what is D? Okay. So I know that in this arithmetic sequence, I should be just adding 6 over and over and over and over again. Okay. See, now I can use this and just plug it back into one of these earlier equations. Okay, like right here, I know that the first term is going to be 41 minus 6 times the 6 that I just found. So what's 41 minus 36? 5. So I know the first term is 5. So now that I have these two items, I can go ahead and plug those in and get my general form. Okay, but there's just one thing. Is everybody okay with what I did? Any questions? Okay. Let me go ahead and take this off. Let's plug in the first term in D. So A sub n is equal to, we found that to be 5, plus n minus 1 times 6. Okay. But here's the thing. We don't want to leave it like this. We want to simplify it so that it's in slope-intercept form, that mx plus b. In fact, tomorrow on the test, I'm going to have you do something real similar. And just in case, I put in parentheses after the blank, slope-intercept form. Okay. So let's see here. What would I get if I distributed 6? 6n minus 6. And we combine my like terms. So the explicit formula should be 6n minus 1. So there we go. That should be able to get me any term in the sequence that I want. Okay. There's my general form, or the explicit form. Did anybody have that correct before we started? Enzo? Good. Anybody else? Okay. Rhett? All right. Very good. Now, what I did for number 2, it's, yes, sir. The test is just straight skills. Like, a couple of problems. I'll say, write me the explicit and recursive form for this sequence. Does this sequence converge or diverge? Given this sequence, find me the certain term. Really, if you feel comfortable with the homework, you should be good. You should be good to go. Okay. All right. Now, for number 2, we're going to do basically the same thing, but it's a geometric sequence. So we're going to write my final answer in this form. Remember, we take the first term times r to the n minus 1. In fact, has anybody solved this one? Does anybody think they know what it is? Half of it? So, Satish, what do you have so far?
I just have to the common ratio.
What'd you get?
-3.
It is -3. Okay, so far, we know we should have -3 to the n minus 1. We just need to know what that first term is. So let's go ahead and see how he got -3. Okay, well, I'm going to do the same thing. The second term is -6, so that tells me n is 2, right? So I'm going to plug into this formula. So we don't know the first term. Okay, Satish has helped us out with the common ratio, but we're going to see how we got that. So we're going to pretend we don't know what that is. So if I were to plug 2 in here, 2 minus 1 will give me 1. So it's just r. What do you think I can set that equal to? -6. We're using n equals 2, so I'm going to set that equal to the second term. Okay. Now, what did I do in the first problem? I solved that for what? I solved it for the first term. So if I just, divide through, I know the first term has to be -6 over r. Now I'm going to do the exact same thing for the fifth term. But I'm going to plug in a 5 there. Okay, so I don't know the first, don't know the common ratio. What would the power be? 4, because the 5 minus 1. And what am I going to set it equal to? 162. That is the fifth term. And then just like before, I'm going to solve that for the first term. See, I'm putting both equations in terms of the same variable. So I'm going to divide by r to the fourth, divide by r to the fourth. Those are going to cancel. So there we go. Where do you think I went from here? Simplify how? Like both those fractions, I know they both equal what? They both equal a sub 1, so what can I do with them? I can set them equal to each other. So I can say negative 6 over r should equal the 162 over r to the fourth. Now, we created a proportion. How do you solve a proportion? Cross multiply. All right, so let's see here. 162r equals negative 6r to the fourth. So the goal here is to get this so that it looks r equals. So the first thing I would probably do is go ahead and divide both sides by r, because the two r's are going to cancel. But again, we want r equals, so I would also get rid of what? So let's go ahead and divide by the negative 6 at the same time, because those two pairs are going to cancel there. So what is 162 divided by negative 6? Negative 27. And remember your exponent rules. If you have a fraction with the same base, what do I do with those powers? Subtract them. So this is r cubed. Now, some other people were getting a little confused about this in previous classes. How do I get an r from r cubed? I take a cubed root. Whatever the power is, that's the index you're going to use. You only take a square root if it's a square, and so forth, okay? Well, luckily, this is a perfect cube. Is this going to go imaginary? No. It only goes imaginary if you have a negative value with an even root. Only if it's even. If it's odd, your answer is always the same as the sign of your radicand. So what is r? FX to t should have already told us. Negative 3. Okay. Well, now that I know r is negative 3, I just start to work backwards and figure out what the first term is. If I know a sub 1 is negative 6 over r, so negative 6 over the negative 3, first term should be what? Positive 2. And in this case, maybe it wasn't really necessary to do that. We're talking about this right here. So to get the next term, like the third term, what would I do? I'd multiply negative 6 by negative 3, right? So what if I just wanted to go backwards? Then I would just divide. So see, it still gave me the first term. All right. Who else needed the key? All right, we got some folks over here. Okay. Questions? Anybody having a hard time? No? Okay. Well, good. We'll take that, put all three somewhere safe. Remember, they're due next week. You are going to get a fourth one, so we're not going to turn them in just yet. Hang on to those. Okay. And let's talk about series. Okay. So what was a series? This is when we took terms from a sequence and we added those up. That's what we refer to as a series. It doesn't matter if it's arithmetic. It doesn't matter if it's geometric. Yesterday I introduced you to this summation notation. This is a Greek letter sigma. When you see that in math, you know you're going to be adding terms together. Okay, that's our sum. Well, the value below, that's the term number you're going to start with. The value above on top, that's the term number you're going to stop at. And what follows, that's the formula to generate the sequence, how to get those terms if you're not already provided those. Typically, we use K or N. When you get to calculus, it's probably not going to be unusual to see I there instead of those. Okay, but the variable, doesn't matter. And we went through several examples. We talked about some formulas. We got into arithmetic series. So here, S sub n, this is the sum of an n number of terms. Okay, so if you know both the first term and the last term, you want to use the top one. But what if you don't know the last term? What other piece of information do you need in order to use the second one? You definitely need to know the number of terms you're adding. You need to know the first term.
The one from behind.
But you need to know the common difference for the second formula. Okay. Now, again, will these formulas be on the test tomorrow? No, they will not. This material is not on the test. Just the last lesson with the homework. Okay. Then we did an example, and we started talking about a geometric series, and I think this is as far as we got, right? Didn't we take the last one and we just wrote it as a summation notation? Okay. So we actually haven't found the sum yet of these 11 terms, but did anybody have any questions over this before we continue? No? Okay, if you do, let me know. All right, well, the formula, if you want to take the sum of a certain number of terms, you take the first term times 1 minus the common ratio to the number of terms, and then you go ahead and divide that by 1 minus the common ratio. So again, it's just a formula. You take your information and you just substitute it in. You only use this formula if it's a partial sum, and I'm going to emphasize that in just a moment. There's something I'm going to have you go back and change. If it's an infinite sum, you will not be using this formula. Okay? So let's see. What was the first term, a sub 1? 4. Okay. Times 1 minus, well, the common ratio was a negative 1/3. Now, how many terms are we adding here? What was n?
11.
N was 11. So, in fact, I could start this by saying the sum of the first 11 terms. So, I'm going to raise that to the 11th, and I'm going to go ahead and divide it by 1 minus the common ratio, negative 1/3. Okay. So it's just a formula. You can plug it in, and from here you could probably go directly to the calculator. I like to try and type in as simple a expression as possible, though. So if there's anything I can easily take care of, like what happens when you subtract a negative?
You just add it.
It's added. Okay. So what is 1 plus 1/3?
Uh,
What improper fraction is that? 4/3. So I'm going to go ahead and replace that with 4/3. Okay. And now let's just type it in and see what the sum of the first 11 terms is. Come on over here to my calculator. Okay, so control divide, 4 parentheses, 1 minus parentheses. I'm going to put in the negative 1/3. Okay, get out of there, raise that to the 11th. Okay. Then I'm going to put divided by the 1 minus negative 1/3 we said was 4/3. Okay. Now here's the thing. As soon as I push enter, I'm going to get this. You know, yours probably went to a decimal, but let me hit control enter. So I'm getting 3.00002. On this one, we want to go ahead and put the exact decimal, what we see. We don't want to go ahead and just put 3 because we're adding up all these terms. Well, even though we have, quite a few places where it's 0, see, that's not entirely correct. See, it'd be the same thing as saying pi is exactly 3. We know it's close to 3, but it's not equal to 3 exactly, right? So we don't want to say the same thing about this sum. For a lot of problems in the future, I'll probably be having you round to a certain number of decimal places. But for this first one, the fact that it says 0.0000, we're not going to go ahead and just say 3. In fact, help me remember this number. What was it? 3.0000169. What was it? Was it 5808?
seems right.
Seems right. 169.35088. Okay, so I was a little off. 35088. There we go. Okay. So that would be my sum. That's a decimal point right here. Okay. Questions on that? Okay. Now, I do want to go back and have you change something on your notes, and it's actually same page. It's right above this. I didn't talk about this yesterday because we really hadn't finished up the problem, but I added a little more information here. Okay, where it says S sub n here on this second formula, you need to mark that out and just put S. It is not technically correct to say S sub n equals the infinite sum, and there's a reason. S sub n is a function of n. So if you're going to write S sub n, the formula that follows would have to have the variable n. Okay, because S is a function of n. S depends on the value of n. Okay, remember this just represents a partial sum. So if you look down here, what variable do you not have in this equation or this formula? You don't have n. So there is a difference between these two. When you see S sub n, You're going to be using this formula because that represents a partial sum. You're only going to be adding a set number of terms. But when you see S all by its lonesome, there's no subscript there, that represents an infinite sum. You're adding an infinite number of terms. And you may see people do this, but it's going to be extremely rare. Like nobody writes S sub infinity. Okay, we just go ahead and write S. Okay. All right, so I just wanted you to go ahead and make a distinction between that. S sub n is just a partial sum. S is the infinite sum. Okay. Now, there are actually several ways to get the infinite sum, and you don't always have to use the formula right here. That's the first thing I'm going to show you. Okay, so let's go to the next page, and let me show you these examples. Now, I did write out a little more here. The sum of the first term to infinity of some formula equals the limit as n goes to infinity of the same summation, which equals S. Now, based on what we just said, is S the partial or the infinite sum? S is the infinite. It's only the partial if it's S sub n. Okay? S is the infinite sum. Now, I just want to make sure you realize this. This is not a true sum. If the series approaches a certain value, then the series converges. In fact, whatever the sequence converges to, that would be the infinite sum. Okay? That's what you're going to end up finding, and I'm going to prove that to you today. All right, so I'll give you a few seconds to go ahead and jot that down, and I'll show you an example. Okay, is everybody about ready? Okay. All right, so example 3, it says, looking at limits of partial sums. For each of the following series, find the first 5 terms in the sequence of partial sums. Which of the series appears to converge? So I'm going to go ahead and tell you that this is based on a geometric sequence. So the first term would be 0.1, second term is 0.01, third term 0.001, and so on. It's just now a series because what am I doing with those terms? I'm adding them up. When I take the terms of a sequence and I add them, then it becomes a series. That's the difference between a sequence and a series. We're adding them up. Okay, well, I could go ahead and apply the formula that I was just looking at, the A divided by 1 minus R to this, and I would be able to get the infinite sum. What I'm showing you here, this is another method to find the infinite sum if you're able to. Okay, so how do we go ahead and find the first 5 terms in a sequence of partial sums? Well, I'm glad you asked. Usually that works out better. Nobody laughed. There you go. Pity laugh. I'll take it. Okay, so what you do is, to generate the first 5 terms in a sequence of partial sums, you always start with the very first term. So I'm going to go ahead and put 0.1, the very first term. Now, to get the second term in the sequence of partial sums, I'm going to add the first 2 terms. So what's 0.1 plus 0.01? 0.11. Now, to get the third term in the sequence of partial sums, I'm going to add the first 3. So what would that be? 0.111. Now, how do you think I'm going to get the fourth term? Yeah, you just keep that pattern going. So I started with the first term, then I added the first two, then I added the first three. Now I'm adding the first four. So 0.1111. So what would the fifth term be? Yeah, 0.11111. And that pattern is going to continue, right? That's how you generate a sequence of partial sums. You start with the first term, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. Now, based on this, hopefully you're going to be able to see a pattern. You're going to be able to notice if this converges or it diverges. Does this look like it's approaching a specific number? Well, what's going to be the sixth term? So there would be 6 ones, right? The next term would have 7 ones. Then we would have 8 ones. So this is approaching a specific number. It's approaching 0.1 repeating. Because every term is just going to give me that many more ones, right? Okay. So here's the thing. Because it does approach a specific number, we say it would what? It converges. In fact, what does it converge to? What is the fractional equivalent of 0.1 repeating? Only one person's known this so far today. Shaman. Okay. So what's the fractional equivalent of 0.1 repeating? That's okay. It's 1/9. Okay. So here's what I'm trying to tell you. Is everybody okay with how I created this sequence of partial sums? Okay. We saw that it was converging. We know it's converging to 1/9. Now, a little side note, the last thing I'm going to do in this lesson is I'm going to show you how to take a repeating decimal without a calculator and write it as a fractional form. I'm not going to do that now because I don't think it's necessary right now. I'm just going to go ahead and tell you 0.1 repeating is 1/9. Okay. But here's the thing. Because it converges, could I take the infinite sum of that series? Yeah. And if I were to take the infinite sum, what do you think that sum would be? It would be 1/9. What it converges to, that would be the sum. Okay. So as of right now, this problem is over. We've got the answer. We know it converges. The infinite sum would be 1/9. Is everybody okay with that? Okay. Now, how many people, by show of hands, are going to be going into calculus next year? Okay, now this is an easier way of doing this. There's another way, a more sophisticated way, that Mr. Heinrich specifically asked me to show you. So if you are not going into calculus, kind of just forget about the next 30 seconds. Okay, don't let it confuse you. If you are going into calculus, this is definitely something that you're going to want to look at. Let's go ahead and write out the notation to see if I would also get 1/9. Let me show you what I mean. We're going to start with this. Now, is S sub n, is that the partial sum or is that the infinite sum? So partial. Okay, we're adding n terms. So I'm going to take this sequence and I'm going to rewrite it using sigma, the summation notation. So I'm going to go ahead and say the sum from the first term to n. See, I can't put infinity because this isn't the infinite sum. And I'm going to go ahead and plug in everything we know. We'll use the form. Remember I said it was geometric? The first term is 0.1. What's the common ratio? What would I multiply each preceding term by to get the next one? Point what? Like 0.1 times what would give me 0.01? It is 0.1. So the common ratio is also 0.1, and then this be k minus 1, right? Now what I'm going to do, I'm going to take this information right here, the first term, and r, and I'm going to plug it into the formula for the partial sum. Remember, this was the formula. The first term times 1 minus r to the n over 1 minus r. Okay, but I'm going to go ahead and change this to fractions. So what is 0.1 as a fraction? That's, ooh, now that's 0.1 repeating, but 0.1 itself is 1/10. So 1/10 times 1 minus, common ratio is 1/10 to the n, all over 1 minus 1/10. See, all I did was plug the information into the partial sum formula. Now, what is 1 minus a tenth?
Point.
Oh, 9. Okay, so 9/10. Okay, so when I'm dividing by a fraction, I'm going to multiply by its reciprocal, right? So this is going to be 1/10 times 1 minus 1/10 to the n times 10 over 9. Well, what can I do now? Does anybody notice anything? Cancel what? The tens will cancel. So what would be the leading coefficient? If those 10 cancel, wouldn't it be? And does that look familiar? Isn't that what we got just a moment ago? Okay. Now we still have this 1 minus 1/10 to the n. Now this is S sub n. This is the sum based on n number of terms, right? Now I'm going to use this very similar to what I had you write up at the very top here with the limit. In order to find the infinite sum, I'm going to take the limit as n goes to infinity of S sub n, of this statement right here. Well, what's going to happen to 1/10 if n becomes infinitely large? He's going to get infinitely small. In fact, he's going to approach what? 0. So what's 1 minus 0? 1 times 1/9. That's the correct mathematical way of showing the infinite sum in this fashion. Now, this right here, will I hold you responsible for that? No. Okay. But those folks going on to calculus, is that something you're going to see again? Absolutely. That's why you got to know the difference. S is the infinite sum. S sub n is the partial sum. Okay. Now, remember, you can only do this if it converges in the first place. If it diverges, you can't do anything beyond that point. Okay. So let's try another example. Okay, so I'm going to leave that right there for the time being. Now, let's say I want to do the same thing for B. I want to find the first 5 terms in the sequence of partial sums, because using that pattern, I want to see if it converges or diverges. If it converges, I can find an infinite sum. If it does not, there's no infinite sum. Right, Ethan? Right. Okay, so how did we generate that sequence a moment ago? What did I start with? Okay, you start with the very first term. So I'm going to go ahead and put 10 right here. Then how do I find the second term? Add the first and second. So that gives me 30. Now the third, add the first 3. 60. Now the fourth, add the first 4. So that's 100. Now it did want the first 5. So what would the next term be in that series? It would be 50. So 50 plus 40 plus 30 plus 20 plus 10. That would be 150. ... Okay. Now, based on the pattern we see, this is the sequence of partial sums. Is it approaching a specific number or no? Okay. It is not. In fact, what are the terms going to continue to do? Yeah, they're going to continue to increase without bound, so it doesn't converge. This diverges. So could I find an infinite sum of this if I wanted to? No. You can only find the infinite sum if it converges. Okay. Let's try another one. Okay. So 1, -1, 1, -1. Okay. So how do I generate the sequence of partial sums? What's the first term? Okay, so 1. How do I find the second term? Add the first 2. So what's 1 minus 1? For the third term, add the first 3. So that's 1. For the fourth term, add the first 4. 0. Now the next one here would be a 1. So what would I get if I added the first 5 terms? It would be 1. And that pattern is just going to continue. That's the sequence of partial sums, right? So what would you say? Is it approaching a specific number? Does it converge? Or is it not? Does it diverge? Jack, you're saying diverge? Okay, would you agree with it? I would agree with them. It's not approaching a specific number. What's it doing? Yeah, it's just oscillating forever. It's bouncing back and forth between two numbers. So this one diverges. Now here's my question. Could I find an infinite sum of that series? No, I can only do so if it converges. Okay, so let's actually go ahead and use the formula here, the formula that you saw a little while ago. Now you'll notice again, I changed it. Cannot be written as S sub n. That represents a partial. So S is your infinite sum. This is another way of using it. But the only way you can use the formula is if the common ratio, its absolute value is less than 1. Okay. So let's go ahead and look at a problem. This one here, determine whether the series converges. If it converges, give the sum. Now, for these problems, if it's an infinite sum, basically I would break it down into 3 steps. Okay. I would first ask myself, does it converge or does it diverge? If it diverges, you can't find an infinite sum, the problem is over. If it converges, then you can continue. Okay. So I would then find the first term and then go ahead and evaluate whatever the infinite sum is based on the formula. Okay. So let's do step 1 here. Now you'll notice, is this one, it's definitely geometric, but what's the common ratio? What does it appear the value is that I multiply by over and over again? 0.75, that's my base, right? So I know R is equal to 0.75. Well, will the absolute value of that be less than 1? Yes. So because that's true, I know that this should converge. Because it converges, can I find an infinite sum? Yes. Okay. Well, let's go ahead and figure out what's the first term. You can probably tell, it's going to be that scale factor. It's 3. But if you're not sure, go ahead and plug in k is equal to 1. So that would be 3 times 0.75 to the 0, because 1 minus 1. And what's anything to the 0 power? 1, and then times 3 is still 3. So now for the third part, let's go ahead and find that infinite sum. You take the first term and you divide it by 1 minus the common ratio. Okay, remember, you can only get here if it converges. If it diverges, problem is done. Okay, so let's see, that would be 3 over 1 minus 0.75, so I'll say 3/4. What's 1 minus 3/4? 1/4. So what is 3 divided by 1/4? 12. So the infinite sum should be 12. All right. Now, because it does converge, could I go ahead and write this out using the calculus method I showed you a moment ago? Absolutely. Now, again, keep in mind, the problem is now done. I've got the infinite sum. This is all I'm going to hold you responsible for. But for those going into calculus, you're going to see it a different way. So I'm going to first say the sum of the first n terms is equal to k equals 1 to n. Remember, it's not infinity because this is a partial sum of 3 times 0.75 to the k minus 1. I'm going to apply this information to the partial sum formula. A sub 1 times 1 minus r to the n over 1 minus r. So this would be 3 times 1 minus 3/4 to the n divided by 1 minus 3/4. Okay. The 1 minus 3/4 I already showed you was 1/4. And what happens when I multiply by the reciprocal? What would the leading coefficient be? 12. And again, isn't that exactly what we got using the formula? Okay. So this would be times 1 minus 3/4 to the n. Okay. Now this is S sub n. Now in order to find the infinite sum, I'm going to take the limit as n goes to infinity of S sub n. So same thing. What's going to happen to the value of 3/4 as n becomes infinitely larger? it's going to become infinitely smaller. In fact, it's going to approach 0. So 12 times 1 minus 0 is 12. Okay. Now remember, I'm not holding you to this portion. Okay. I just want to make sure everybody that's clear. Yes. The partial sum is only adding a specific number of terms. The infinite sum is adding every term to infinity. You keep going. Well, see, we don't know. We don't know the number of terms because it's infinite. We can't get an exact number. It's going to keep going forever. But we can get a really good approximation of what the sum would be if I added them all up. Yeah. Mm-hmm. Now, you remember this formula that I just used right here? Okay, this guy? I could apply it to that problem we did previously. In fact, let me go back over here and show you. This one right here, where we got the answer to be 1/9. Okay. If you look at the original sequence here, the first term was 1/10, right? The common ratio was 1/10. Is the absolute value of 1/10 less than 1?
Yes.
Yes, so I can use that formula. I can say the first term, 1/10, divided by 1 minus r, 1 minus 1/10. Well, what's 1 minus 1/10? 9/10. Let me go ahead and take that out. And I'm going to multiply by the reciprocal, so that gives me 1/10 times 10/9. And what do you notice? What's my answer? 1/9. What did we get before? Did we get 1/9? Okay. I'm just wanting you to see that there are two different ways, at least, that you could find that infinite sum. Okay. The method I would probably go with is going to be using the formula, but you can create a sequence of partial sums like we did here. How we doing? Any questions? Anybody confused by anything? Okay. Then we'll pick this up on Friday. Tomorrow is our test, and we will see how much further we're able to get. Okay. Let me go ahead and shut it.